This is our course Introduction to Algorithms and topic Space Complexity, Measure and Algorithm. In addition to analyzing time complexity, evaluating space complexity is important for designing efficient algorithms and programs. Space complexity refers to the total memory space needed by an algorithm, including both auxiliary space and space used by inputs. This article will provide a comprehensive and beginner-friendly introduction to analyzing space complexity. So, what's the space complexity? When we need design an algorithm to solve a problem, it needs some computer memory to complete its execution. For any algorithm, memory is required for the following purpose. First, to store program instructions, to store constant values, to store variable values, and for few other things like function calls, jumping statements, etc. So generally, when a program is under execution, it uses the computer memory for three reasons. They are as follows. So first, instruction space. It's the amount of memory used to store complete compiled version of instructions. Second one, environmental stack. It's the amount of memory used to store information of partially executed functions at the time of function call. Third one is data space. It's the amount of memory we use to store all the variables and constants. Total amount of computer memory required by an algorithm to complete its execution is called a space complexity of that algorithm. So to calculate the space complexity, we must know the memory required to store different data type values according to the compiler. For example, the C programming language compiler requires the following: 2 bytes to store integer value, 4 bytes to store floating point value, 1 byte to store character value, 6 or 8 bytes to store double value. If any algorithm requires a fixed amount of space for all input values, then that space complexity is said to be a constant space complexity. If the amount of space required by an algorithm is increased with the increase of input value, then that's space complexity. The space complexity is said to be linear space complexity. Big O notation for space. Like time complexity, space complexity is formally measured using Big O notation. O f of n denotes that the space used is at most f of n for an input size of n. Common space complexities include O of first, So it's a constant space used regardless of input size. O of n linear space usage proportional to input size. O n to the power of 2 is quadratic space usage. O of log n is logarithmic space usage. For instance, an in-place sorting algorithm uses O of one space, while a sorting algorithm that makes a copy of the input uses O of n space. Comparing time and space complexity. While both time and space complexity are important, time complexity generally receives more focus during algorithm analysis and optimization. Some key differences between analyzing the two. Time complexities like O of quadratic n or O log n express how a running time grows with input size. Doubling input size has a precise measurable effect on running time. Space complexities like O of n are often rough approximations since actual memory usage depends on several factors like data types, memory allocation schemes, or etc. Optimizing the time complexities has an obvious impact on performance. So improving from O of quadratic n to O of n log n speed has a major effect on runtime. The impact of space optimization less direct. Reducing from ON to ON or auxiliary space improves memory usage but has a less direct bearing on speed or user experience. Time and space analysis both provide valuable perspectives into an algorithm efficiency. A balanced approach looks at both while recognizing time complexity and reveals more about the algorithm's core performance and scalability. Thank you.